Hello everybody and welcome to yet another math video. This math video is for college algebra / algebra 2. And in this video we're going to dive a little deeper into what happens with polynomials and more specifically their graphs. Up until this point, polynomials have been nicely factorable, where you've been able to find the zeros by factoring and then plot them and base some sketch of a graph based on the multiplicity at the x-intercepts and the graph's end behavior, and possibly y-intercepts. Well, in this video, we look at polynomials that are still factorable, but they don't look to be factorable. All of the factoring methods you've learned up until this point won't help you factor these polynomials. So a couple things we look at are 1, the factor theorem. 2, we will use the, I'll go over how to use the factor theorem to factor polynomials. Then I will go ahead and use the rational zeros theorem so that we can factor the polynomial without needing any hints. In order to factor it, you'll see what I mean in a few seconds. And then we'll use the rational zeros theorem to graph polynomials, because we still want to be able to graph polynomials even though they may not look factorable. All right, let's jump into it. So let's go over the factor theorem. The factor theorem states if f of c equals 0, then x minus c is a factor of that function. And one thing I want to point out here really quick is that this is an x value. X would equal that number, which you can find if you set the factor equal to 0 and solve for x. X would equal c, just like it does right here in the function. So just a little bit more notation or vocabulary here. This is the factor. This is what we would call just c. That's what we would call the zero of the function. So it's weird, we state the factor theorem like this, and then we lead with the factor. We're basically asking, is this binomial a factor of f of x or g of x? And there was one thing I wanted to change here. This should be 25. All right. So all we have to do then is we have to figure out what value are we substituting in for x into our function. This doesn't tell me what x equals, but if we find the corresponding 0 for this factor, which would be 5 if you add 5 to both sides, then we can start evaluating this function. So f of 5 will be 3 to the 4th minus 15 to the 3rd minus 5 plus 25. So all of these x's are being replaced with 5s. And then we can see that this will be 5 to the 4th power is 625. 625 times 3 is 1,875. And you can follow that process all the way down, and see that we get 0. And that's the magic number, 0. You're so happy you can go ahead and put a little smiley face in there, because this tells us that x minus 5 is a factor of f of x. All right, so checking to see if something is a factor is pretty easy. Go ahead and pause the video, try this one for yourself. See if x minus 5 is a factor for this polynomial. So here you can see, if you again set the factor equal to 0 and solve and find the 0 associated with this factor, and then use that 0 to substitute into the function, you get 5 cubed is 125, 5 squared is 25, 5 is 5, go figure. And then when you combine all of these numbers together, you get 90. And 90 is not 0. So x minus 5 in this case is not a factor of g of x. All right, so let's see how we can use this to help factor polynomials that may not immediately seem factorable. So how to factor using the factor theorem. So in this instance, I'm going to tell you that x plus 1 is a factor of this function right here. And the only way, at least that my students know at this part in the course, the only way my students know how to factor a polynomial with 4 terms is to factor by grouping. So let me group up the first two. I'll do this. There we go. So there go the first two. Here go the last two. And you want to try to find a common factor from the first two and from the last two, and hopefully you end up with the same set of parentheses. And I'm telling you right now, it's not going to happen. So how can we use this fact, that x plus 1 is a factor of this function? How can we use that fact to factor f of x? All right, well, we know f of x factors because x plus 1 is a factor. I told you that's what it was. So we know this. So here's the actual function, here again. And if it can factor, that means we can turn it into the product of 2 or more factors. So here's one factor and here's something else, but we don't know what this is. What is this other factor? Well, it turns out you can solve for this other factor, this something. We could just divide by x plus 1. So let me show you what that looks like very, very small like. So if I divide this side by x plus 1, this entire factor cancels here, and x plus 1 on the left side of this equation. And you can see that we would end up with something would be equaling 4x cubed plus 15x squared plus 10x minus 1, all divided by x plus 1. Okay, so from the last lesson, or from a previous lesson, seeing a polynomial being divided by another polynomial means we will get to use polynomial division to figure out what this something is. Even better, since we know that this is a factor of the function, if we divide these two things, we should get no remainder because it will divide evenly. That's what a factor does. A factor can divide into its function evenly. So polynomial division, but even better, we can use synthetic division to figure this out. And synthetic division is much, much faster. So let's take a look at how that will work on the next slide. All right, so from the previous slide and me saying it already, we have this division happening, and here we go, we have this to figure out what the other factor would be. So we divide this using synthetic division. All right, so here I'm going to take the coefficients of the polynomial in the numerator without skipping any powers of x. So let me circle those here. I will have 4, 15, 10, and negative 1. So 4, 15, 10, and negative 1. From there, we have to have an x value to put in the corner. Now this kind of works like finding the 0 of the function. So that's why we set the denominator equal to 0 and solve for x. That would give us the negative 1. So here I'm going to write my x would be negative 1. We can't put the whole factor in there. You can't write positive 1. That doesn't mean anything. But if we can find the 0 associated with that factor, That's what we're looking for. All right, so we can take the -1 and do the synthetic division. So let's do this here. We can bring down the 4. -1 times 4 is -4. Add those together and get 11. So then I can do -1 times 11 is -11. And what does that give me? -1. Then finally we have -1 times 1 times -1 would give me a +1. And lo and behold, as I said on the last slide, if we know a factor of a polynomial, we should end up with a remainder 0. So again, from a previous lesson, you should know that this translates to 4x squared plus 11x minus 1. And that equals our something. So where did that go? There we go. Equals the something. So what does that tell me? What that tells me then is our function from the previous slide, f of x equals 4x cubed plus 15x squared plus 10x minus 1 is the same thing as writing the factor x plus 1, right? The factor is the whole denominator here, times what we got as our answer after division, 4x squared plus 11x, minus 1. And I guarantee if you take the time to multiply all of both of these polynomials together, you'll end up with this function here. So one thing you'll get from this lesson is, are we there yet? Are we finally done? So here's an issue with the factoring. Students in the past, in my experience, have decided, oh man, one synthetic division, that was enough. This was enough for me. But I see a factor that is quadratic. You always, always, always have to be checking any quadratic expression. Will it factor? From here on out, will it factor? Does this factor? Well, luckily for everybody out there, this does not factor anymore. So in fact, I'm just going to go ahead and call this a prime polynomial, because it does not factor anymore. But as we go through a couple more examples in this video, you have to always be checking. Oh, I got something quadratic. Does it factor? Oh, it does? Then you actually have to go through and factor it. If it doesn't, you just leave it alone. Let's take a look at another example. On this slide, it's a little bit different, right? We have these directions. Completely factor f of x if x plus 3 is a factor of this thing. So again, you still have a little bit of information about this function, right? You know something about it. This is given to you. X plus 3 is a factor. So that means I should be able to multiply x plus 3 times another polynomial and get 3x cubed plus 7x squared minus 7x minus 3. You could also check me if you want by setting this factor equal to 0 and solving for x, and then substituting this value into the function. And you should get 0. Let me verify that very quickly. So when you multiply all this out, 3 times -3 cubed, you have to cube the -3 first, then multiply by 3, you get -81. This gives you 63, this gives you 21, this is of course -3. Add these together, it's 84, subtract 84, you get 0. Okay, so yeah, for sure, x plus 3 is a factor. All right, so what do we do then? I already found, because I set the factor equal to 0, I already found the corresponding 0 that is associated with this factor. So what you need to do then is take that 0, x equals -3, put that in the corner, take the coefficients of the function. So I've got 3, 7, -7, -3. And then go through and see what polynomial we're left with. 3. -3 times 3 is -9. Add those together. -3 times -2 is +6. Add those together is -1. -3 times -1 is +3. That's 0. Fantastic. All right. So here, what this means then, if I use or interpret this answer to be 3x squared minus 2x minus 1, I can say now that the function is equal to the factor we were given times this new polynomial we got after dividing. Okay, here we go. Are we there yet? Nope. I see something quadratic. Have to check to see if this quadratic expression factors. All right, so let's see here. That is a times c. Again, here's a, here's b, here's c. It is already in standard form. So a times c is -3, and b is -2. So I'm trying to find two numbers that multiply to -3 that add up to -2. I think it's -3 and 1. Whoa, so this does factor, because -3 plus 1 is -2. All right, so since it factors, you go through and factor this polynomial accordingly, and you will get 3x plus 1 times x minus 1. So the whole function now can be completely factored in this form. And that's it. If I guarantee, if you multiply all of this out correctly, you will end up with exactly what we started with in the original function. And again, your previous methods for factoring fail you here. You cannot factor this by grouping, well, easily anyway. So we have to figure out this new method of how it works. Final reminder, if you have something quadratic, you must check to see if it factors again. And then going back to an earlier lesson, we could also find the zeros for this polynomial. It's generally a lot easier to do if you have it already factored. Like this 0 would be x equals -3, and we had already found that over here. But the 0 that corresponds with this factor would be x equals 1, and the 0 that corresponds with this factor would be -1/3, -1/3. So these are the zeros. These up here are the factors. All right. Now we get to go over into the rational zero or rational root theorem, and we'll explain more on the next slide. So the rational zeros theorem, aka the rational root or roots theorem, it is used when you don't have any information about your function. So before the last couple examples, you were given some information like, here's a factor. You could also be given information like, here's a 0. And we take that information away from you. You have it no longer, and you can no longer just start dividing. So the basic idea is, behind the rational zeros theorem is, we create a list of possible zeros, this word, possible zeros, by dividing all factors of the constant term by all factors of the leading coefficient. So I'm going to do some highlighting here. So constant term, let's see, factors of the constant term, and factors of the leading coefficient. So I want it to be known that right here, the leading coefficient is 1, and the constant term is 10. So off to the side here, what I'm going to do is I'm just going to say, or I guess below, 10 over 1. And your goal is to figure out what numbers can you evenly divide into 10. That being 1, 2, 5, and 10. And I'm kind of half truthful here with you because you can also evenly divide 10 by -1 and -2 and -5 and -10. But we're going to save all of those negatives for the end. So in the top, the factors of 10 are here. In the bottom, we have the factors of 1. Well, that's pretty simple. It's just 1. So what do you do with this? Is you create a list of numbers. I'm going to take every number in the numerator from the 10 and divide it by every number in the denominator. So here's what I'm going to do. I'm going to say, why don't we say 1 divided by 1. Okay, that's 1. 2 divided by 1. That's 2. 5 divided by 1. That's 5. 10 divided by 1. That's 10. And I wanted to move it over just a little bit, so I did. So what happens is if you have more than one factor in the bottom, like this 1, I would cross this out and I would start dividing again. And you'll see what happens in a later example. But that's it. I divided everything in the numerator by each factor in the denominator, and we're done. There are no more factors in the denominator, so this is my complete list. Now, to make sure we go back and encapsulate all of those negative numbers I mentioned earlier, we have to put some nice curly braces around this because that's how you represent a set of numbers. And in front of this set of curly braces, we just put a plus or minus. And that's it. We have created a list of possible zeros by dividing here. Well, great. How does that help? We have this list of zeros. What do we do with it? So the way this process works, now that we have some information here, right? We didn't have any information about this function, but we created a list of possible zeros. So we pick one. We pick one. All of these zeros are x values, x equals, and they correspond to some factors that we can look at soon. So I'm just going to kind of randomly pick one. I think I'm going to pick, let's pick -10. So I'm going to say x equals -10. And we do a synthetic division until we find a 0 in this list that works. That gives us a remainder 0. So here I have 1 as a coefficient, -4, -7, and +10. Here I go. Let's see. I'm going to bring down the 1. That's our first step every time. And I'm going to multiply that 1 by -10 and get -10. Add -4 and -10 to -14. Multiply -14 by -10. Get +140. I don't think this one's going to work out that well. This is 133, -1330. And that gives me a remainder of -1320. All right, so that remainder is not 0. We want a 0. All right, so back to the drawing board. And I get to cheat a little bit here because I have a tablet in front of me. I can just erase these numbers. You may or may not erase these numbers. I don't know. So let's pick a different value. Let's pick a different x value. What do you say about, let's pick a -2. So 1 times -2 is -2. Add those together to get -6. -2 times -6 is +12. Add those together, get 5. -2 times 5 is -10. Hey, we got a 0. So what does that mean for us? That means x equals -2 is a 0. But that also means that x plus 2 is a factor. So I'm taking the time here to write out both of these. This is the 0, and this is the corresponding factor that goes with this 0. If you set this equal to 0 and solve for x, hey, guess what? You'll get this. So how does that help? Well, we have our function now. This will be f of x equals x plus 2 because we just found this factor using our list of numbers that we generated on the previous slide. What is the other factor here? Well, the other factor is this one right here. It would be x squared minus 6x plus 5. Okay, so I see something that is linear. Whoops. Linear. And something that is quadratic. You guessed it. Does this factor? Does the quadratic factor, in this case, yes, so you can factor that on your own, but it factors to the following: x minus 1, x minus 5. So there, we have completely factored f of x. Now, once you completely factor f of x, it is very easy to find the zeros like we did in the last example. The zeros here would be x equals 2, here, x equals 1, oh, this is a -2, my bad, and x equals 5. Guess what else we can do? We can call these with multiplicities. So we can say multiplicity 1. Here we can say multiplicity 1. Here we can say multiplicity 1. Now, why would we be interested in the multiplicities of these zeros? Let's go through a couple more examples, and I'm sure it'll be clear by the end of the video. So here we are. We're going to put it all together from the top. We're going to use the rational roots or zeros theorem to factor this polynomial and find zeros. We're going to do it all in one. So the first thing we need to do is create the list. Create a list of possible zeros. And so what I have to do then is I have to take all of the factors that will divide evenly into 6 and divide it by all of the factors that will divide evenly into 2. So this is what it's going to look like this time. 1, 2, 3, 6. So to create my list, I'm going to say this will equal, whoops, plus or minus. I'm going to take all of these values in the numerator and divide them by 1. So that's pretty simple. They just show up again. 1, 2, 3, 6. Now I'm not done. I took all those numbers and divided by 1, so I'm going to cross that one out. Oh look, there's another factor in the denominator this time. So I have to take all of those values and divide them all by 2. But I'm only going to add them to the list over here if they're a new number that's not already in this list. Okay, So here I have 1 divided by 2 is 1/2, that is not in my list. 2 divided by 2 is 1, that is already in my list. 3 divided by 2, that's new. And 6 divided by 2 is 3, that's already in my list. And we're done with 2. And that's it, we don't have any other numbers to divide by. So here is my list of zeros. So we created a list of possible zeros. There it is. Now, when you are picking a zero for synthetic division, I'm going to give you all a little bit of advice on which values you want to pick first. Use synthetic division to find a zero for the function. So we have to pick a number. Now, I know everybody and their brother and their mother and their sisters and fathers do not like to work with fractions. In this case, your fear is well founded. I would say do not start with fractions. So while they are a part of the list, I would say don't use fractions. The next thing is you definitely do not want to start with large numbers. So maybe 6 is an actual zero for this polynomial, but I don't want to start there. I want to start with numbers that are going to be easy to use with synthetic division. And lastly, you probably don't want to work with negatives, but if it comes to it, you might have to work with negatives. All right, so I'm just going to run through a few synthetic divisions here. I'm going to start with 1. Okay, 1 did not give us a 0. Let's move on to 2. Ugh. 2 does not give us a 0. I'm thinking we may have to pick a negative number. Let's see. Let's pick -1. Yikes. I hope I pick one. I'm running out of space. Oh, thank goodness. All right. So x equal to 2 is a 0, and I've been meaning to write this here every single time, and I have been failing at that, but these are all zeros that go in the corner here. So we have one, we found one. So x equals -2 is a 0. That means x plus 2 is the corresponding factor. Let's continue this on the next slide. With the fact that we know that x plus 2 is a factor, x equals -2 is a 0 corresponding to that factor, and that 2x squared plus 5x minus 3 is the other factor that we need to go along with this one. Cool. Are we there yet? Nope. All right, so we factor this thing. This is f of x equals x plus 2, and here we have 2x minus 1 and x plus 3. Yeah, so this is how we factor this particular quadratic. So way down here I can add those two factors, 2x minus 1 and x plus 3. Neither of these new ones are quadratic, so we're done factoring. Yay! Lastly, we can put these zeros over here. The zero that corresponds with this first green factor is 1/2. The zero that corresponds with this second green factor is -3. Guess what? All these zeros have multiplicity of 1. So I'm just kind of leaving that there for right now, but they all have multiplicity 1. You can see that right here from all of these exponents. So that means these would all cross the x-axis, yeah? Remember doing all that? All right, let's look at the next example. So here we have another example. The directions look a little different. That is, find all real and imaginary zeros for this function. And essentially what I'm going to do in addition to this is I will also be factoring this function because it's just like a byproduct of finding zeros. So let's begin. Let's find our possible zeros here. So our constant term is -36, and our leading term, our leading coefficient, is 3. So we take all of the factors of our constant term, and that will be 1, 2, 3, 4, 6, 9, what else? 12, 18, and 36. Some numbers have a lot more factors than others. And we will divide them all by 1 and 3 because those are the numbers you can divide evenly into 3. So our list over here will be plus or minus. If you take the entire list in the numerator and divide by 1, it just gives you the list in the numerator. So 1, 2, 3, 4, 6, 9, 12, 18, and 36. Now, the next, so that means we're done here. So then I'm going to take every number in the numerator and divide it by 3 and add only the new ones. So that'll be 1/3, 4/3, what's next? 3/3 is 1. Oh, I forgot 2/3. I normally do them in order. 6/3 is 2, we have that. 9/3 is 3, we have that. 12/3 is 4, 18/3 is 6, and 36/3 is 12. So it looks like we're done. We don't need that comma. All right. So we're done with 3, and we've made our list. Again, you want to be starting with lower numbers. You're more than welcome to try 12 if you want to, or -18, or heck, you can even do positive or -4/3. But the smaller numbers are going to be easier to do the synthetic divisions with, so I'm just going to start with 1, see if that works. Got 1, 3, -7, 6, and -36. This is not 0 when you add them together, so 1 is out. Now I'm going to randomly pick a 0 and hope that it works out. Something like x equals 3. Sure, seems random enough to be right. 3, -7, 6, and -36. All right, here we go. 3, 9, 2, 6, 12, 36. Would you look at that? 0. So we know this is the 0 for this function up here, and we know x minus 3 is the factor. And the other factor, like we've been saying, is down here. This would be 3x squared plus 2x plus 12. All right, so I can write this function up here as f of x equals x minus 3 was our factor, and the other factor was 3x squared plus 2x plus 12. All right, so here we have to check. This is quadratic. Does this thing factor? This time, no, it doesn't factor. So this is as factored as the function will get. This is what we would say is completely factored. Cool. Our goal, though, up here said to find all real and imaginary zeros for this function. We already know one of the zeros, so I'm going to make my list here. Let's do this in purple, I like purple. So our zeros for f of x are 3. That's all we know right now from that one. Since we cannot factor this one nicely, what we have to do then is solve it a different way. So we use the quadratic formula. So let's do this off to the side. There's A, B, and C. So we can use the quadratic formula. It is negative b plus or minus the square root of b squared minus 4 times a times c all over 2, oops, not 2a, 2a, there it is. All right, so I can do a lot of this for you. This is negative 140. When you simplify everything in the square root, you get negative 140 all over 6. You can simplify the square root as 2 plus or minus. You can divide 140 by 4. That's the largest perfect square number you can divide into 40. And you will take the square root of that 4 and get a 2 outside of the square root. The negative comes out as an I square root of 35. And then you can simplify this fraction if you can divide every number outside of the square root by the same number. So if you divide all these by 2, you'll see that we get negative 1 plus or minus I square root of 35 all over 3. So here are the 3 answers you were expecting to get anyway, because I'm going to bring this back to your attention. The largest exponent in a standard form polynomial tells you how many answers you should be getting. We have 1 here, and we have 2 here, 1 with the plus, 1 with the minus. So if you're asked to find all real and imaginary numbers, or zeros, that doesn't necessarily mean there will be imaginary zeros. It just means there's a chance you'll be using the quadratic formula to figure those zeros out. So welcome to the granddaddy example. We have one more. These directions are a little bit different. Pretty simple. Graph this polynomial. Well, we are going to do exactly everything we have done before. We're going to start by finding our list of numbers. So I will create my list. So I'm going to start here. I know the factors of 4 are the same factors of 4. Fine. And I'm going to divide them all by 1. I'm going to divide them all by 2. So that'll give me 1/2. 2 over 2 is 1. 4 over 2 is 2. Those are already in the list. So I'm done with 2, and I'm going to take all of the numbers in the numerator again and divide them by 4. So that'll give me 1 over 4 is 1/4. 2 over 4 is 1/2. 4 over 4 is 1. So there is my list, and these are the possible zeros. So I'm going to pick one. Actually, you pick one. You try it. Pause the video. I'll come back in a few seconds with a good synthetic division for you. Okay, So here is the dealio. 2 is a 0 for this particular function. So what does that mean? We have a factor of, we have a factor of x minus 2, and we have another polynomial here that would be 4x cubed minus 3x squared minus 9x minus 2. Now here's the fun part to this. I keep asking in multiple previous examples, are we there yet? Can we factor this quadratic? That is a problem because this isn't quadratic. This is cubic. So we have to do this whole process again. All this same process, we have to do it again. So just for the red part, I'm going to come off to the side. I'm going to create my list of zeros. It'll be this. Let's see. 1, 2, 1/2, 1/4, and I believe that's it. I took the numbers 1 and 2 and divided them by 1, 2, and 4. And I got this list. So just for the red part, if I run another synthetic division, and yes, you have to find a second 0 here, I'm going to pick 2 again, and this will be 4, -3, -9, and -2. Bring down 4. This will be 8 minus, positive 5. This will be a 10. That leaves me with a 1. Multiplied by 2 is 2. Add those together is 0. This is good. We're looking for the zeros. So now I have a factor of or factored form of this function would be x minus 2, another x minus 2, times, and I'm going to put this one in blue, 4x squared plus 5x plus 1. See, now we have to, now we have something quadratic, and we can see if this factors. So I want to point something out before I finish this on the next slide. You take a look here, 2. The degree in here is 2. The degree is the biggest exponent. The degree up here was 4. 4 is 2 more than 2. So that means we were going to have to go through and do 2 synthetic divisions. It could be that if you had a degree 6 here, 6 is 4 more than 2, which means you would have to go through 4 synthetic divisions before you get something that was quadratic. So for every 1 more that the degree in the original function is bigger than 2, that's how many synthetic divisions you'll have to get through. Let's finish this up on the next slide. So with the last little bit here, you can see that this quadratic does indeed factor into these 2 polynomials, or these 2 factors. And yes, now we are done factoring. So the final factored form here would be f of x equals, we can combine these together into x minus 2 squared times 4x minus plus 1 times x plus 1. Now the original direction was to graph this polynomial. So that means we have to go back and get our zeros, and our zeros are going to be 2. Let me use some colors here. 2 from this polynomial, or from this factor, it'll be -1/4. From this particular polynomial, and it will be -1 from this factor. So from there, all we have to do then is figure out the multiplicity of each and the behavior of each. So the multiplicity for the first 0 is 2, and the multiplicity for the others are 1. The last bit, we need to make sure we have the correct behavior. That will bounce and these will cross. So over here on my handy dandy coordinate plane, I have to find these zeros on the x-axis. So there's 2, and it will bounce at 2. Here's negative 1/4 approximately, and it will cross there. And here's negative 1, and it will cross there. The end behavior here for this particular polynomial function, if I add all these up, I get a degree of 4, but really we care that this is even. And we have a positive leading coefficient. So that means the positive tells me the right side will go up, and since the degree is even, the left side will do the same. So I'll go up here and up here. I know I cross the x-axis at negative 1 and 1/4, and if I come back and connect back to the other 0 at 2, you can see it will automatically bounce. So here's the graph of the polynomial we started with. It was a lot harder to factor, not impossible. In fact, not even that much harder. It was just longer. But we need to get to that factored form so we can make our ZMB chart, find the end behavior, and get to graphing. All right. I hope that it explains everything that you need, and good luck.